Black holes can pack more mass than the Sun into a region the size of a city, and they're not even the only invisible things out there. In this video we'll meet the cosmic wallflowers, true darkness that bends light, tugs on stars, and sometimes flashes like a lonely lighthouse just to prove it exists. You'll learn, in plain words, what makes something dark in space, how astronomers find things they can't see, hint, we watch what they do to their neighbors, and why these shadowy objects matter to the story of the whole universe. A black hole is simply a place where gravity is so strong that light can't climb out. Think of it like a cosmic drain with a point of no return. Dark matter is the invisible stuff that holds galaxies together, like the hidden beams inside a house you can't see but that stop the roof from collapsing. Brown dwarfs are failed stars, the light bulbs that never quite turned on. Neutron stars cram a sun's mass into a city-sized ball so dense a spoonful would outweigh a mountain. One of those would ruin your day, but they're also the universe's coolest lab coats for extreme physics. We'll use everyday images, whirlpools, footprints in snow, and broken light bulbs, to make sense of the strangest things in the sky, throw in a few surprising visuals, and even crack a tiny joke or two. Stay with me and you'll leave knowing how the universe hides its secrets, how we catch them, and why these dark players might decide the fate of galaxies, and maybe the fate of the universe itself. Black holes, masters of darkness. A black hole is a region in space where gravity gets so strong that nothing that crosses a certain boundary can come back out, not even light. Forming when large amounts of mass are tightly packed into a very small volume, some black holes come from collapsed stars, while others sit at the centers of galaxies and are vastly more massive. Think of it like crumpling a giant star down until its gravity wins the day. The result is a compact object that dominates its neighborhood. These compact masses range from being only a few times heavier than our Sun to objects that outweigh entire star cities by millions or billions of times. The edge around a black hole is called the event horizon, and it marks the point of no return. Cross it and information about what went in can't get back out to the rest of the universe, which is a strange and final kind of privacy. Inside that boundary, most descriptions use the idea of a singularity, an area where our usual physics stops giving useful answers because the mass is extremely concentrated. Close to a black hole, clocks tick differently compared with far away. Time stretches and slows. A simple way to picture it is that gravity pulls on time itself, so observers far away and those near the hole do not agree on how fast things happen. We usually spot black holes by what they do to nearby matter, not by seeing the hole directly. Gas and dust falling toward one heat up and glow, making bright disks of light called accretion disks. This is where astronomers pick up strong 10th rays. Stars orbiting an unseen central mass can also point to a hidden black hole, much like watching leaves circle a whirlpool tells you where the drain is. Colliding black holes announce themselves by sending ripples through space, known as gravitational waves, which instruments can detect as a faint shiver across vast distances. Light from background objects can bend around a black hole too, creating warped images, similar to how a straw looks bent in a glass of water. Falling toward a black hole would be dramatic and final. Tidal forces stretch and squeeze objects, an effect often nicknamed spaghettification. The nearer you get, the stronger the stretch becomes, and it's not something you can recover from. Despite the dramatic reputation, black holes don't go roaming the galaxy eating everything in sight. They act according to local gravity, so unless our Sun suddenly wandered close to one, Earth would not be in immediate danger. On the larger scale, black holes play active roles. Spinning black holes and their magnetic surroundings can launch powerful jets of particles, like cosmic garden sprinklers on steroids, and those jets can affect how galaxies grow and shine. Black holes remain places where current knowledge bumps against unknowns, and that is part of their appeal. They are laboratories for testing gravity under extreme conditions, and studying them helps us understand how matter behaves at the limits. A healthy mix of curiosity and caution is the right approach. Fascinated from a safe distance, and maybe don't volunteer to go on a field trip. Supermassive black holes at galactic hearts. At the center of most large galaxies sits an object so heavy that its pull shapes the motion of nearby stars and gas, its mass can equal millions or even billions of suns. In plain language, this is a place where gravity gets so intense that nothing nearby can easily escape, not even light, which is why it appears black to us. The name people use is long, but the idea is simple: a tiny, incredibly dense region that dominates its neighborhood. We find these giants by watching how things move around them. Stars that orbit very quickly and oddly close to the galactic center give away the hidden mass, much like watching cars race around a roundabout tells you something big is hidden behind the hedges. In our own galaxy, the central object has about 4 million times the mass of the Sun. Another famous one in a different galaxy is measured at roughly 6.5 billion solar masses. When gas and dust fall toward these objects, they spin into a flat, glowing whirl, similar to water circling a drain, and that hot, bright swirl is one of the clearest signs that matter is falling in. Think of it as cosmic cooking: the faster the stir, the hotter the pan. The visible part, the glow and sometimes spectacular jets of particles streaming away at nearly light speed, comes from material getting chewed up before it crosses the point of no return. That point of no return is like an invisible edge. Once you cross it, escape is essentially impossible. You can picture it as a one-way door with terrible customer service. Despite containing so much mass, the actual region small enough to trap light is tiny compared with the size of the whole galaxy, like a dense cobblestone in the middle of a vast plaza that nonetheless controls the traffic flow. Powerful outflows and jets launched from the area around the central object can reach far beyond the galaxy's center and change how gas cools and forms stars, so these central heavyweights help decide whether their host galaxy is calm and star-friendly or hot and sleepy. Observers use many tricks to study them, tracking star orbits to map the hidden mass, watching flares of light when fresh gas plunges in, and linking radio dishes around the world to effectively build a planet-sized camera that can reveal the shadow cast by that invisible edge. That global camera once produced the first direct picture of the dark region around one of these monsters, confirming ideas that had previously been tested only on paper. Scientists care about these objects because they are labs for extreme physics and because they seem to grow alongside their galaxies, like stubborn roommates who rearrange the furniture. Current work focuses on sharper images, monitoring rapid changes in brightness, and understanding how the biggest jets affect entire galactic neighborhoods. The better we watch them, the more they teach us about gravity, matter under stress, and how galaxies evolve. Plus they give astronomers ready-made excuses to build ever larger telescopes, which is always fun. Stellar mass black holes, deaths of massive stars. When massive stars run out of the fuel that keeps their cores hot, the pressure that normally holds the core up suddenly disappears and the center collapses inward under its own weight. If the inner core is heavy enough, nothing can stop that collapse and the core compresses into a region so dense and compact that its gravity creates a point of no return. Light itself cannot escape from inside that boundary. Sometimes the outer layers explode away in a bright blast, throwing out the star's outer shell and leaving a compact remnant behind. Other times the collapse is quieter and much of the star simply falls in, a failed firework rather than a grand finale. Astronomers spot these compact remnants in a few clever ways. A black hole feeding on gas from a nearby star will form a spinning, glowing disk that shines very brightly in 10th rays, like a stovetop coil on high. We detect that high-energy light even though the hole itself is invisible. If a bright companion star wobbles unusually as it orbits an unseen partner, its motion tells us there's a heavy, invisible object tugging on it. Ripples in space, tiny stretches and squeezes that travel outward when two stellar mass black holes crash together, can be picked up by precise instruments on Earth and confirm the existence of these objects in a completely different way. Think of the ripples as the space version of dropping a pebble in a pond, but with far stranger physics and far fewer ducks. These black holes carry a lot of mass packed into a surprisingly small volume, several times, or even many times, the mass of the Sun squeezed down to roughly the size of a city. Because they are so compact, their gravity near that edge is enormous, and anything that comes too close is pulled in. They grow by swallowing material, gas from a companion star, debris from a disrupted object, or by joining with another black hole in a head-on meeting. The growth process can produce fierce jets and lightning-fast flows of matter that are easier to see than the black hole itself. Those jets are like a shaken soda bottle spraying streams of glowing particles into space. Studying how massive stars die and leave behind these objects gives practical insight into how the universe recycles matter. The explosions that often accompany core collapse fling heavy elements into space, seeding future generations of stars and planets, while the compact remnant can change the fate of a binary system or stir its surroundings in dramatic ways. In everyday terms, a massive star's death can be gentle or dramatic, quiet or explosive, but either way it reshapes the neighborhood, and occasionally behaves like a cosmic Roomba that eats everything within reach, but without the helpful flashing light. Intermediate mass black holes, the missing middle. Some black holes tip the scales at a few hundred to a few tens of thousands of times the mass of the Sun, placing them squarely between the smaller, dead star remnants and the monstrous giants that sit at the centers of galaxies. They are heavier than the black holes left behind by single dying stars, yet far lighter than the supermassive ones that dominate galactic cores. Think of the difference like vehicles. A stellar black hole is a compact car, a supermassive one is an aircraft carrier, and these middleweights are the delivery trucks, not tiny, not gigantic, but important for hauling things around. Several believable ways exist for such middleweight objects to appear, and none require breaking the laws of physics. In dense star clusters, many massive stars can collide and merge repeatedly, a bit like a snowball rolling downhill that keeps gathering more snow until it's surprisingly huge. Another route is the direct collapse of a large gas cloud. If a chunk of gas falls in fast enough without fragmenting into lots of stars, it can form a massive object that collapses into a black hole. A third path is simpler bookkeeping. Many smaller black holes can merge over time, building up mass step by step, like small debts combining into a mortgage. These different stories are not mutually exclusive. Nature probably uses a mix of them. Finding these objects is tricky, which explains the nickname missing middle among scientists who like tidy classifications. One approach is to watch gas falling onto a black hole, because that gas heats up and shines in 10th rays and other wavelengths. A bright point of high-energy light in the right place can hint that something heavy is gobbling material. Another method is to follow the motions of stars. If stars orbit faster near the center of a star cluster, something massive and invisible might be tugging on them, similar to seeing leaves swirl faster around a drain and inferring there's a whirlpool. More recently, instruments that detect ripples in space itself, called gravitational waves, can pick up the final screams when two black holes collide, and some of those signals point to mergers involving intermediate masses. The obstacles are many. The sphere of influence of a middle-mass black hole can be tiny on the sky, the signals can be faint or confused with bright clusters of stars, and sometimes ordinary stellar activity mimics the expected signatures. It's like trying to spot a dim candle in Times Square during New Year's Eve. Why should anyone care about this elusive middle? Because they may be the missing step that explains how the universe's giant black holes grew so big. If intermediate examples are common, they offer a natural ladder for growth. If they're rare, then galaxy centers must have had a very different upbringing. They're also practical targets for current and next-generation observatories, telescopes that see high-energy light, precise measurements of star motions in clusters, and gravitational wave detectors each bring a piece of the puzzle. On a human level, learning whether the universe produces many mid-sized black holes or skips straight from small to huge would change our story about how galaxies assemble, like discovering whether neighborhoods grow by adding houses or by suddenly dropping in apartment blocks. Finding the missing middle would be satisfying science, and maybe a little like finally locating the one sock that always disappears from the laundry. Primordial black holes, relics from the early universe. Slightly denser patches in the very early cosmos could have collapsed under their own gravity and become black holes before stars ever existed. These objects would be born from the texture of the infant universe rather than from dying stars, meaning their origin story is different even if their appearance can be similar. The key idea is simple: if a region was packed tightly enough, gravity could win over pressure and make something that traps light. Think of pressing dough into a dense knot. The tighter the knot, the more it holds together. Some of these early-born black holes could be tiny, while others might be quite large. Tiny here doesn't mean the size of an atom necessarily, it means much smaller than the black holes formed when stars die. Small ones behave differently because of a quantum effect that lets them slowly leak energy. This leaking is often explained with a playful comparison: a big teapot holds heat a long time, while a tiny kettle cools fast. Over enormous spans this process can cause small black holes to shrink and vanish, while large ones sit around practically forever. Detecting these relics is like detective work with very subtle clues. One method looks for the way their gravity bends light, acting like an invisible magnifying glass when a background star lines up behind them. In daily life it's similar to how a glass of water distorts the view of something behind it. Another method listens for ripples in space that arrive when two compact objects smash together. Instruments on Earth can pick up those ripples as faint signals. Scientists also search for sudden flashes of particles that would come from a very small black hole finishing its slow evaporative life, although none of those dramatic finales has been confirmed. The practical payoff would be huge if even some of these objects exist in significant numbers. They could explain part, or maybe a lot, of the unseen mass we call dark matter, or they might simply be rare cosmic leftovers that tell us about conditions in the universe's first moments. Current observations put limits on how many there can be and what sizes are allowed, so many possibilities are squeezed but not ruled out. In the meantime, the idea remains delightfully speculative, like finding crumbs from the universe's earliest baking session, and future observations will tell whether those crumbs are a handful or just a light sprinkle. Event horizons, the point of no return. A black hole's boundary is the region where the speed needed to escape equals the speed of light, so once anything, matter or light, goes past that invisible line, it cannot get back out by ordinary means. This boundary is not a solid wall, it is a mathematical surface defined by gravity and motion, like an invisible shoreline where the current is faster than any swimmer. Think of it as a one-way street for everything. Larger black holes have a larger boundary, smaller ones are tighter and meaner. From far away, objects falling toward that boundary appear to slow and fade, because the light they give off gets stretched and weakened on its way to an outside observer. Very long, faint signals. Up close, though, a person crossing the boundary would not suddenly hit anything or feel a sign that says, "No return." Local physics still works normally at the crossing itself. Tidal forces, those stretching and squeezing effects of gravity, decide how violent the experience is. For a small black hole the tides are extreme and you would be stretched like taffy. For a supermassive one the tides near the boundary can be gentle enough that you wouldn't notice anything immediate. Practical clues to the boundary come from how matter behaves nearby. Hot gas spins around, light bends into tight loops, and some photons race along paths that almost circle the hole before escaping. This region creates a dark silhouette against bright gas, and telescopes that combine signals from many instruments can pick up that outline and the motion just outside the boundary. Quantum effects add a twist. Tiny particles can be produced just outside the boundary and lead to a faint glow from the hole over unimaginably long timescales, so the no escape rule has a subtle exception in the quantum world. That's a mind-bender. It's also where deep puzzles about information live. Astronomers use those nearby motions, stars orbiting an unseen center, gas jets, and ripples in spacetime from colliding holes, to infer where the boundary must lie, even though the boundary itself doesn't emit light. Observations plus the math of gravity let scientists map out where the point of no return sits. In everyday terms, it's like noticing the wake of a very fast boat and deducing the boat's path without ever seeing the hull directly. And while the idea of an inescapable edge sounds ominous, it gives physicists a very practical laboratory for testing how gravity and quantum rules interact. No protective gear required, thankfully. Black hole shadows and images. Telescopes do not capture the black hole itself, they reveal a dark silhouette created when light from surrounding gas and dust is either swallowed or bent away. The dark center is the shadow, an absence of photons, while the bright ring around it comes from superheated gas racing near the edge, glowing like embers around a campfire. Light that gets close can loop around the hole several times before escaping or falling in, producing a narrow, intense ring that astronomers call the photon ring. Think of it like a fast-running river. Leaves that approach the drain either spiral in or get flung backward, and the patterns left behind trace where the water can no longer return. Creating the actual pictures requires more than one telescope. Observers use a technique that links radio dishes around the planet so they act like a single, Earth-sized instrument. The method combines tiny bits of signal collected at many sites, similar to assembling a jigsaw from scattered pieces. Noise from the atmosphere and gaps in the data make the reconstruction hard, so teams rely on clever algorithms to fill in missing parts, much like restoring a scratched photograph. Polarized light measurements add another layer of detail by mapping magnetic field lines. This is a bit like wearing polarized sunglasses to see glare patterns, but for cosmic weather instead of bright reflections on a lake. Different black holes show different behavior in their images. A very massive, slowly changing source can produce a steady, symmetric ring, while a smaller, more active one flickers and shifts as the flow of hot gas changes rapidly. Mass mainly sets how large the shadow appears on the sky, whereas spin can nudge the shadow's center and make the bright ring brighter on one side because of the Doppler effect. Gas moving toward us looks brighter, like a passing car's headlights seeming stronger as it approaches. Observations of the bright ring and its asymmetries help scientists infer how matter is falling in and whether strong magnetic fields are present to launch jets, the narrow, powerful streams that some black holes shoot out like cosmic fire hoses. Seeing a shadow at all is a triumph of technique and interpretation, but it's not a simple photograph. It's a reconstructed portrait built from radio waves, simulations, and theory. Future improvements aim to add more telescopes, use higher frequencies, and even put receivers in space to sharpen the view, in other words, to turn a grainy selfie into a high-resolution portrait. The payoff goes beyond pretty pictures. These images let researchers test how gravity bends light under the most extreme conditions and learn the rules for how matter behaves when pushed to the edge. And while the result isn't a spooky eye staring back at us, it is a dramatic and useful glimpse of where the normal rules of our everyday life break down, like watching the weather at the edge of a hurricane, only much farther away and far more mind-bending. Hawking radiation. Do black holes evaporate? Black holes are not perfectly black. They give off a whisper of particles and energy due to tiny quantum effects right at their edge. This happens at the event horizon, the point of no return around a black hole where gravity wins and even light can't climb out. In simple terms, space is never truly empty. It's more like a restless sea where pairs of particles constantly appear and vanish. Sometimes one of those particles falls into the hole while its partner escapes, and the escaping one is what we call the emitted radiation. Think of empty space as a party where guests keep popping in and out for just a second. Usually they leave together. But if the party is next to a big whirlpool, the black hole, one guest can get sucked in while the other bolts away, free. That runaway guest carries energy with it. Because energy and mass are linked, when the black hole loses that energy it slowly loses mass too. So over immense stretches of time it can evaporate, like a slow cosmic candle. The process is extremely feeble for ordinary black holes, though. You wouldn't notice it on any human timescale. Smaller black holes act differently than huge ones. The smaller the black hole, the stronger this leak becomes, and the more energetic the escaping particles are. So a tiny black hole would glow hotter and fade faster. Big black holes, the kind sitting in galaxy centers, leak so faintly that their glow is drowned out by everything else around them. That's one reason why no astronomer has yet pointed a telescope and said, "There it is, Hawking radiation." Laboratory experiments have created analogs of this behavior using fluids and light, and those tabletop systems show similar effects, which help scientists gain confidence in the theory even without direct cosmic detection. This idea blends gravity with quantum fuzziness. You can picture it as nature's bookkeeping. When a particle escapes, the black hole must account for the lost energy. The accounting results in a tiny shrink. Over unimaginable periods, if a black hole doesn't gain more mass from stars or gas, it will eventually finish evaporating and leave behind only radiation. That outcome is certain in the math, but the universe is messy. Black holes usually eat more than they lose. So most of them grow or stay steady rather than quietly vanish. Researchers still treat this as one of the most interesting bridges between two big ideas, gravity and the quantum world. Mini experiments that mimic event horizons and careful observations of cosmic environments help test the predictions, and clever theoretical work explores what happens at the very end of evaporation. In plain language, yes, under the rules we use now, black holes can evaporate, but it's a process so slow and subtle that for everyday purposes a black hole behaves like a very long-lived heavyweight champion that's only breaking a sweat. Information paradox: what happens to lost matter? Black holes give off a faint glow known as Hawking radiation, and that simple fact is what creates the real puzzle. If a black hole can evaporate away, what becomes of the detailed information about the atoms and fields that fell into it? Information in physics means the exact arrangement and state of a system, the microscopic recipe behind what we see, and unlike a grocery list, physics normally insists that this recipe is never truly destroyed. Think of it like a photograph. The pixels might blur, but the information that once formed the picture can, in principle, be recovered if you know how the blurring happened. A useful everyday comparison is burning a book. After the fire you have ash, smoke, and heat. The clear story printed on paper looks gone. But in principle the ash and the pattern of escaping gases and photons carry traces of the original arrangement of ink and paper molecules. The problem with black holes is that the radiation they emit appears perfectly thermal, like the uniform warmth from a toaster, so it seems to carry no trace of the original book's words. That would mean a fundamental rule of quantum physics, which says you should be able to track information forward and backward in time at the microscopic level, is broken. That contradiction is the heart of the information paradox. Several ideas try to resolve the tension, and they use friendly metaphors so the physics doesn't feel like a lecture. One idea is that the outgoing radiation is not perfectly random after all. It carries tiny, hidden correlations that, if you had infinite patience and an impossibly good detector, would let you reconstruct the original content. Picture throwing a pebble into a pond and watching the ripples. At first glance the pattern is messy, but the ripples still know something about the pebble's size and where it landed. Another idea borrows from how a hologram works. All the information about the three-dimensional object could be encoded on a two-dimensional surface around the hole. This is like finding that the label on a shipping box somehow contains the entire inventory list inside. Strange, but mathematically plausible. Some alternative proposals are messier. One suggests the black hole doesn't evaporate completely but leaves behind a tiny remnant that hoards the information, like a squirrel hiding away all your lost socks. That leads to its own headaches because such remnants would have to be very weird to store arbitrarily large amounts of information. Another more dramatic suggestion is that the boundary of the black hole becomes hostile. So-called firewalls would fry anything trying to cross, though that idea creates uncomfortable clashes with the simple notion that falling into a large black hole should feel uneventful at first. These contrasting pictures show why the problem is still debated. Every resolution trades one headache for another. Practical work in theory and laboratory analogs has nudged opinion toward the idea that information is preserved and somehow encoded in the outgoing radiation, but there is no direct tabletop experiment with real black holes to hand. Researchers build experiments with waves in water tanks or with ultra-cold atoms to mimic event horizons and watch how analog, Hawking, radiation behaves, which is a clever way to test the logic without needing to lob a book into an actual black hole. The payoff for solving this is more than cosmic curiosity. Understanding how information survives extreme gravity sharpens our grasp of quantum mechanics and could influence future ideas in quantum computing and secure information, though you should not expect black holes to become data centers anytime soon. Accretion disks, bright light around dark hearts. Gas and dust falling toward a compact object flatten into a spinning disk that shines with fierce light. Friction and collisions between particles act like cosmic rubbing, turning motion into heat. The hotter the gas, the bluer and more energetic the light it gives off. As the material spirals inward it moves faster and smashes into neighboring streams, so the inner regions glow in powerful 10th rays while the outer rings glow more gently in visible and infrared light. This change from hot to cool across the disk creates a layered glow, much like the bright core and dimmer edges of a flame. Think of the disk as a celestial washing machine where the clothes are tiny particles of gas and the spin is relentless. Water down a drain is a simple, familiar comparison. Everything circles faster near the center and slower farther out. Small clumps can form temporary traffic jams that show up as bright spots racing around the disk, and astronomers can track those movements to learn how fast things orbit. That motion also explains why some disks flicker in brightness. One moment calm, the next moment a hotspot zips by and the light jumps. The center itself, though, can remain dark because the compact object at the heart, like a black hole, doesn't let light escape from its deepest part. In that sense, the bright disk is a halo of borrowed light, powered by material that gives up its energy before crossing the invisible boundary. This process of turning falling matter into light is remarkably efficient. It squeezes a lot of energy out of mass, far more than ordinary burning does, and that efficiency is why disks around compact objects can outshine entire regions of a galaxy. Telescopes that see different colors of light are needed to read this story, because 10th-ray instruments show the searing inner ring while optical and infrared instruments reveal the cooler outskirts. Everyday examples help make the picture less alien. A lava lamp gives a similar sense of blobs rising, cooling and sinking, and a racetrack shows how speed depends on radius. Scientists also compare the disk's turbulence to weather. There are winds, waves, and eddies that move heat and material around. A little humor helps too. These cosmic rings are like the universe's own brightly lit roundabouts, where the cars are atoms and the toll to get closer to the center is a burst of light. Jets and blazers, when darkness becomes loud. Powerful beams of matter and light blast out from the edges of hungry black holes, sometimes pointed almost directly at Earth. These focus streams, called jets, carry particles and energy away at speeds so close to the speed of light that strange effects make them look much brighter and faster than they really are. When one of those beams lines up with our line of sight, the object appears extremely active and noisy across the sky. Astronomers give that special name to such objects, and they are among the brightest steady sources in the universe at many wavelengths. Think of it like a cosmic flashlight aimed at you. A little tilt and the beam lights up your wall, while a straight-on hit can be blinding. The engine that launches these streams is a simple-looking but violent setup. Gas swirling into a black hole forms a spinning, glowing disk, and magnetic fields thread through that disk like rubber bands. Those magnetic fields act like funnels and catapults, channeling some of the infalling gas into narrow jets that shoot away instead of falling in. A helpful everyday image is a garden hose with the thumb partially covering the end. The water speeds up and narrows into a jet. Replace water with charged particles and your thumb with magnetic fields, and the garden hose becomes a black hole feeding zone. The result is a beam that can stay well collimated over vast distances, sometimes appearing to travel straight through an entire galaxy. Light from these aligned jets is boosted in both brightness and apparent rapidity by effects related to their extreme speed. This is similar to how the siren of a passing ambulance seems higher or lower as it zooms by, except with light and with much more dramatic consequences. Because of that boosting, blazers, the face-on type, show rapid changes in brightness, flickering on timescales as short as hours and sometimes less. In practical terms, that is like a lighthouse whose beam randomly pulses faster and slower. Observers detect emission all the way from radio waves up to gamma rays, and often see the light coming in a particular polarization, meaning the light waves line up, much like a neatly combed hairdo compared with a ruffled one. Studying these loud, dark engines teaches us about how black holes grow and how they shape the galaxies around them. For instance, jets can push material out of a galactic center, affecting star formation in a way not unlike a strong wind scouring leaves off a lawn. Astronomers track this feedback to piece together how galaxies evolve. Famous examples help ground the idea. Objects such as BL Lacerti and 3C279 are well-known blazers that have produced bright, variable flares observed across the globe and from space. And yes, while the phrase "darkest objects" sounds ominous, these systems are paradoxically some of the loudest beacons in the sky, cosmic blowtorches that, if they could talk, would probably shout. Photon spheres and gravitational lensing tricks. Near a very compact mass, gravity can be so strong that even light is forced into curved paths instead of straight lines. Astronomers call the special loop where photons, particles of light, can circle a black hole a photon sphere, a narrow shell of space just outside the black hole's dark edge. For a non-spinning black hole, that shell sits at about 1.5 times the black hole's point of no return, the event horizon. That orbit is not like a stable planetary track, it's razor-thin and delicate, and a tiny nudge sends a photon either spiraling inward to the abyss or flinging outward into space. Think of the photon sphere like a car skidding on a circular icy track. Stay perfectly balanced and you circle around, wobble just a bit and you slide off. A marble precariously balanced on the top of a rounded hill offers another picture. It can sit for a moment, but the smallest disturbance sends it rolling down. In the same way, light near the photon sphere can loop around multiple times before escaping, which is why the area around a black hole can appear unexpectedly bright in a narrow ring. That bright ring is more than pretty cosmic wallpaper, it's an observational fingerprint. When hot gas and dust swirl near a black hole, some light falls straight in, some takes bent shortcuts, and some schemes the photon sphere, making many tight loops and arriving at our telescopes concentrated into a thin, bright outline. Telescopes tuned to the radio band can pick up that outline as a ring-like structure, which tells astronomers not just that a black hole is there, but also about how strongly it bends light and how matter behaves in that extreme neighborhood. On larger scales, mass acts like a lens and bends light traveling past it. That's gravitational lensing in a nutshell. A convenient kitchen table comparison is a straw and a glass of water. The straw looks broken because light changes direction when it goes from water to air, and gravity does a similar trick by curving spacetime so light changes course. When a massive galaxy or cluster sits between us and a faraway object, the background object can appear stretched into arcs, multiplied into several images, or even smeared into a near-perfect ring when the alignment is just right. Those lensing effects are more than visual oddities, they're practical tools. Astronomers use the magnification from galaxy clusters as a natural zoom lens to spot very faint, distant galaxies that would otherwise be invisible, much like using binoculars to read a sign across a field. On a smaller scale, microlensing, a brief brightening when a star and possibly planet passes in front of another star, has helped reveal planets that hide far from their suns and would be hard to find any other way. Gravitational lensing also acts as a mapmaker, letting scientists infer where invisible mass, like dark matter, must be to bend light the way it does. The photon sphere and gravitational lensing are cousins in the family of gravity's light-bending tricks. The photon sphere creates an intense, close-in ring right by the black hole, while lensing stretches and multiplies images across vast cosmic distances. Both depend on the same basic idea: gravity changes the paths of light, and both give astronomers surprising, useful views of the invisible, the edges of black holes, the structure of galaxies, and even planets you couldn't spot otherwise. So no, you can't go for a swim in a photon sphere, but you can enjoy the cosmic contortions of light and the clever ways scientists use those contortions to learn about the universe, and yes, gravity is quite the practical prankster. Rogue planets drifting in cosmic night. Not all planets stay tied to a star, some drift alone in the dark, lonely stretches between the lights. These solitary worlds are often very cold on the outside because they no longer get warmth and light from a sun, so their surfaces can be frozen solid like a forgotten pond in winter. Astronomers sometimes call them rogue or free-floating planets, and the idea of a planet that never rises or sets for a star is both unsettling and oddly poetic. They can be as small as Earth or as large as Jupiter, and whether one is a lonely ice ball or still glowing faintly from leftover heat depends on how it formed and how recently it was kicked out of a system. Planetary wanderers can come into being in two main ways, and both are easy to picture with a quick household example. One route is ejection. In a busy planetary system, the gravitational tugs are chaotic, like dozens of marbles in a bowl bumping into each other until one flies out. A close gravitational encounter with a bigger sibling, or a collision during a stormy youth, can fling a planet out into interstellar space. The other path is formation on its own, from a small clump of gas that collapsed without becoming a star. This is similar to how very small failed stars called brown dwarfs form. The border between a tiny brown dwarf and a massive planet is fuzzy, so scientists often debate whether a particular free object started life in a disk around a star or formed all by itself. Finding these dark travelers is a challenge, because they emit little or no visible light. One clever method used by astronomers is called gravitational microlensing. When a rogue planet passes exactly in front of a distant star, its gravity briefly bends and magnifies the star's light, making the star look brighter for a short time. It's a bit like holding a magnifying glass over a distant candle and seeing the flame flare up as you move it. Teams that search the sky for microlensing events watch millions of stars and wait for the rare, temporary brightening that signals something passing in front. Other approaches rely on infrared surveys that can catch relatively warm, recently formed objects glowing from leftover heat. The WISE mission, for example, helped reveal many cool brown dwarfs and other faint objects in our neighborhood. Still, the faintest and coldest rogues are essentially invisible to most telescopes, like embers under ashes. Could a wandering planet host life or at least pockets of liquid water? It's not impossible in principle. A large planet with internal heat from its core, plus a thick insulating atmosphere, could keep subsurface oceans liquid beneath a shell of ice. Think of a thermos keeping soup warm, but on a planetary scale. Moons, if present, might provide additional heating through tidal forces, much like Jupiter's moon Io is warmed by gravitational squeezing. Surface life that depends on sunlight, however, would not get very far, not ideal for sunbathing or growing tomatoes. Scientists treat these ideas cautiously, they're interesting hypotheses rather than established facts. Rogue planets matter because they teach us about how planetary systems evolve and how violent those early days can be. Observing them helps fill in the story of planet formation and migration, and it forces us to refine models that predict how many planets a typical star might form and then lose. Future surveys and space telescopes designed to catch microlensing events or to look deeper in infrared light will improve our census of these wanderers. For now, the concept of a planet adrift, silent, cold, and alone, remains one of the more striking reminders that the cosmos is a place of motion and escape, not just orderly orbits. Brown dwarfs, failed stars that hide in infrared. Not quite a star and not quite a planet, a brown dwarf sits in between those two familiar types of objects and carries traits of both. They have more mass than planets like Jupiter but not enough to keep a steady hydrogen-burning furnace going in their cores, which is what makes true stars shine. If an object packs roughly 13 times Jupiter's mass, it can briefly burn a type of hydrogen called deuterium, but it takes something closer to about 75–80 times Jupiter's mass before stable hydrogen fusion starts and you get a proper star. Think of a brown dwarf as a campfire ember. It glows and gives off heat, but it never becomes the roaring bonfire that a star is. Most of the light from these objects comes out in infrared, the warm, long-wavelength light your TV remote uses to talk to your television. Because they are relatively cool, brown dwarfs are faint in visible light and hide from ordinary optical telescopes. That's why astronomers use infrared surveys and instruments to find them, scanning the sky for faint heat signatures the way a night vision camera spots a warm body in the dark. Some are as warm as a hot oven, while others are as cool as the inside of a refrigerator, so the amount and color of infrared they emit can vary a lot. Their atmospheres are mini laboratories of strange weather. Hotter brown dwarfs can have clouds made of tiny bits of iron and rock, while cooler ones show clear signs of methane and water vapor, the same molecules you find in Earth's atmosphere and in natural gas, but under very different conditions. Spectral classes labeled L, T, and Y are just convenient names astronomers use to group brown dwarfs by temperature and chemistry. L-types are relatively warm with cloudy skies, T-types show methane absorption, and Y-types are the coldest and most unusual. You can compare it to clothing: someone wearing a heavy coat, someone in a t-shirt, and someone bundled in pajamas. Each tells you about the weather they're experiencing. Brown dwarfs show up in different settings. Some drift alone through space like lonely hikers. Others are companions to stars, orbiting like distant relatives who show up at family gatherings every once in a while. There are even brown dwarfs with their own planetary companions, blurring the line between planet and star system. Because their atmospheres overlap in temperature and composition with gas giant exoplanets, studying brown dwarfs helps scientists understand exotic worlds around other stars without the glare that often hides planets. Finding and studying them is a bit of detective work. Astronomers combine infrared images, measurements of motion across the sky, and analysis of the light spectrum to confirm a brown dwarf's identity. It's similar to identifying a person on a low-resolution camera by their gait, their height, and a distinctive hat. Multiple clues build a convincing case. Instruments on the ground and in space that are sensitive to infrared light have opened up this field, letting researchers measure temperatures, chemical fingerprints, and even weather patterns on these objects. Practical reasons for caring about brown dwarfs go beyond curiosity. They provide test cases for models of how stars and planets form, and they act as natural laboratories for atmospheric physics under conditions we don't experience on Earth. In other words, what we learn from brown dwarfs improves our understanding of giant exoplanets and helps refine the tools used to characterize them. And for the romantically inclined, brown dwarfs are like the universe's shy relatives, dim, cool, and occasionally revealing surprising complexity if you look closely enough. Black dwarf stars, the universe's future embers. No truly cold, dark ember of a star has been spotted yet, because the leftovers of ordinary stars take an unimaginably long time to fade to that state. Stars like the Sun burn by fusing lighter atoms into heavier ones and eventually shed their outer layers, leaving behind a hot, dense core called a white dwarf that no longer makes energy by fusion. Over time that core radiates away its heat and slowly cools, just as a coal in a campfire will stop glowing and become a lump of cold ash. Think of a white dwarf as a glowing stovetop burner after you turn the flame off. A black dwarf would be the burner long after it has gone completely cold and you have to stop checking it every 5 minutes. A black dwarf would be small and heavy for its size, roughly as compact as a planet but holding mass similar to a star, and mostly made of carbon and oxygen. Instead of shining, it would sit in space as a dark, dense object. You wouldn't see it unless something else lit it up or it passed in front of a background light. The way it resists being crushed is odd but simple to picture. Imagine a crowded elevator where people are packed so tightly they won't let the floor collapse. In stars it's the electrons squeezed together that keep the ball from collapsing. That pressure doesn't come from heat but from the fact that matter is packed as tightly as it can be, which keeps the object stable without any ongoing fusion. If a black dwarf ever met trouble, like stealing mass from a nearby companion star or smashing into another compact object, it could wake up again and become bright, possibly producing violent eruptions. The same basic idea applies to white dwarfs today. Add enough material and nuclear reactions can start or an explosion can happen. So these dead embers are not necessarily the absolute end, they are more like a very tired phone that can still spring to life if someone plugs it into a powerful charger. In practice, though, such encounters are rare and depend on the local neighborhood the black dwarf inhabits. Because none have been observed, black dwarfs live in the realm of careful calculations and patient prediction. Finding one would be like discovering a fossil that tells you how the slowest parts of stellar life behave, and it would teach us about how matter behaves when it is crammed together and allowed to cool for eons. For everyday life, they are a cosmic curiosity more than a practical concern, but they are also a reminder of how the universe evolves on timescales far longer than human lifetimes, rather like reading a very long, very slow novel whose last chapters most of us will never see. Neutron stars and pulsars, compact and ominous. A collapsed star can shrink down to something the size of a small city while still carrying more mass than the Sun, so dense that atoms no longer look like what we know. Their electrons are squeezed into nuclei and neutrons end up packed shoulder to shoulder. These objects are only about 10 to 20 kilometers across in diameter, roughly the distance a commuter might drive in 20 minutes, yet they hold the weight of a star. That extreme packing gives them properties we don't see in everyday life, so it helps to compare. Picture a rock compacted so tightly that its interior behaves more like the inside of an atomic nucleus than ordinary matter. Density is one of the easiest ways to feel how strange they are. A spoonful of this material would weigh about 1 billion tons on Earth, an amount you can't really lift, even with a crane the size of your problems. Surface gravity is enormous, strong enough that if you dropped something it would smash into the surface at a significant fraction of the speed of light, and the pressure inside is enough to crush atomic structures flat. Magnetic fields around these objects can be trillions of times stronger than Earth's, which is like comparing a refrigerator magnet to a superhero magnet that would scramble your phone from halfway across the solar system. Some of these compact remnants become pulsars because they rotate and sweep beams of radiation into space like cosmic lighthouses. If the beam crosses our line of sight, it appears as a regular flash, pulses that arrive with such clock-like precision they can outmatch many human-made timepieces. The rotation periods vary a lot. Some spin slowly, like a relaxed merry-go-round, while others rotate hundreds of times each second, closer to a blender on high setting. The mechanism is simple in concept. Charged particles are funneled by the strong magnetic field along the poles and produced as narrow, fast beams. When the beam points toward us, we see a pulse. Astronomers use these pulses for practical work. They can time the arrivals to test ideas about gravity, to search for ripples in spacetime, and to even think about navigation away from Earth, a kind of space GPS that leans on pulsing stars instead of satellites. Pulsars also show sudden hiccups in rotation called glitches, where the spin jumps a tiny bit, as if the star sneezed and rearranged its interior for a moment. For a human-friendly analogy, think of a spinning top with a small dent. Most of the time it spins smoothly, but occasionally it jerks and then keeps going, and astronomers take careful notes when that happens. These objects are ominous in the poetic sense but fascinating in the practical one. They are laboratories for physics under conditions we cannot create on Earth, and they behave in ways that stretch common sense while still obeying the same physical rules you learned in school. A little humor helps. If a neutron star were at your backyard barbecue you'd probably notice. The grill would be the least of your problems, but from safe distances they're incredible beacons that help us measure and understand the universe. Magnetars, the ultramagnetic lurkers. Certain collapsed stars pack magnetic fields trillions of times stronger than Earth's, and that fact alone makes them some of the strangest objects in the sky. They are born from the same processes that make neutron stars, squeezing a mass similar to the Sun into a sphere just a few kilometers across, so the material is fantastically dense. Their magnetic fields are typically in the range of 10^14 to 10^15 Gauss, which is a way of saying ordinary magnets, like the ones on your fridge, are laughably weak by comparison. Close up, those fields would twist atoms into odd shapes and make charged particles spiral in ways no kitchen magnet can manage. Because their fields are so extreme, these stars behave like cosmic drama queens occasionally throwing tantrums. Crustal stresses build up as the magnetic field shifts, and when the star's brittle outer layer cracks, think of a ceramic plate under pressure, the sudden motion releases a huge burst of energy. Those bursts show up as powerful flashes of 10th rays and gamma rays that space telescopes pick up. Short flashes can outshine the brightness of many entire regions of the galaxy for a moment, and even though that sounds alarming, such events are rare and happen far away. The magnetic grip on charged particles forms a complicated magnetosphere around the star, where particles are trapped and whirl at tremendous speeds. This environment creates steady 10th ray glow and occasional outbursts. The steady glow is like a campfire, the outbursts are the sudden bonfire that catches everyone's attention. Studying these emissions gives scientists a laboratory for physics that cannot be reproduced on Earth, how materials behave under crushing pressure and mind-bending magnetism, for example. That's useful even if no one plans to build a magnetar in their garage. Practical consequences for daily life are negligible because all known examples are extremely distant, but understanding them helps improve our general knowledge of extreme environments, which in turn sharpens the tools astronomers use across the board. The same detectors that catch magnetar flares also monitor other high-energy phenomena, and refining those instruments leads to better observations of many cosmic events. So while you won't need a warning sticker about magnetar proximity on your phone, these ultramagnetic lurkers remain compelling to scientists and, frankly, pretty entertaining to think about. Quark stars and exotic compact objects. Some compact objects could contain matter crushed so tightly that individual protons and neutrons dissolve into their building blocks, quarks. In that state, called deconfined quark matter, the usual picture of distinct particles breaks down and you get a single, dense soup of quarks moving almost freely. This idea leads to the possibility of quark-rich stars, where most of the interior is made of this exotic soup rather than ordinary nuclear matter. Think of it like taking a tightly packed brick of cereal and smashing it until the flakes melt into a paste, only far more extreme and without the milk. One practical way to picture a hybrid star is to imagine a peach, a familiar outer flesh of neutrons surrounding a hard, different core made of quarks. Hybrid stars are a middle ground between ordinary neutron stars and a full quark star. Strange quark matter is a related concept where a mix of quark types, including the heavier, strange, quark, could form a stable state. If that were true, entire stars might be made of it. The terminology sounds scary, but the basic idea is simple: particles rearrange under pressure into a new, denser packing. A home analogy, like rearranging stacked books into a single dense block that occupies less shelf space. Other exotic compact objects expand the menu beyond quark-based ideas. Boson stars are a theoretical class made of particles that like to share the same state and act together, rather like a huge, cold quantum blob held together by gravity. Gravastars are proposed alternatives to black holes where a thin shell surrounds a weird vacuum interior instead of an event horizon swallowing everything. Picture a water balloon with a tricky inside and a hard outer skin. Each of these models predicts different behavior for the object's surface, how it glows, and how it reacts when it merges with something else. In everyday terms, two bells of different materials make different sounds when struck. Astrophysical mergers are the cosmic equivalent, and the sound is picked up as gravitational waves and light. Why do these possibilities matter? Because distinguishing a true black hole, a neutron star, or some exotic object affects how we understand extreme physics and matter under pressure. Observations that could help include pulses of radio waves from spinning stars, 10th rays from hot surfaces, and the ripples in spacetime produced when two compact objects collide. Some models even suggest subtle signatures like delayed echoes in the gravitational wave signal or unusual cooling patterns after a burst of heat, though detecting those is tricky and requires careful analysis. Picture two tuning forks struck together. The combined tone might reveal whether one fork has a hidden crack. There are real hurdles to proving any of this. Many exotic models predict effects that are small or easily mimicked by more ordinary objects, and our measurements must be very precise. Instruments like radio arrays, 10th ray telescopes, and gravitational wave detectors are the modern toolset, and they keep improving. Laboratory experiments with particle collisions can recreate aspects of the quark soup at high temperature, but not the cold, ultradense conditions inside a compact star, so theory and observation must work hand in hand. Scientists joke that building a quark star on Earth would ruin your neighborhood, so for now we rely on telescopes instead. In practical terms, the search for quark stars and other exotic compact objects is a detective story with many clues but few smoking guns. Careful modeling, clever data analysis, and multiple types of observation increase the odds of spotting something genuinely novel. If nature has chosen one of these exotic forms, we might learn new rules about how matter behaves when pushed to its limits, and that would be one cosmic surprise with a very small punchline: the universe really does enjoy packing things tighter than your closet. Dark nebulae and interstellar dust clouds. Far from the bright pinpricks of stars, thick clouds of gas and tiny solid particles drift through space and can completely block the light behind them. These clouds are mostly made of very small grains, soot-like bits of carbon, bits of rock similar to sand, and thin coatings of frozen gases, so small that each one is closer in size to smoke than to a pebble. You can think of them like cosmic dust bunnies. The grains clump together and hang out in the cold, dark places between stars, forming patterns that range from faint wisps to dense, black patches that swallow starlight. Light from background stars disappears when it passes through these clouds because the grains both absorb and scatter visible light. That process also makes the light that does get through appear redder, much as sunlight turns redder at sunset after passing through Earth's atmosphere. The effect is similar to driving through heavy fog where headlights look dim and orangey, only in space the fog is made of microscopic particles and the color shift tells astronomers about the dust itself. Some of the most striking examples look like silhouettes, dark shapes sitting in front of bright star fields, because the dust is so opaque in visible light that it creates clear, dramatic outlines against glowing gas or star clusters. Inside the densest pockets, conditions change and chemistry happens. The dust shields the interior from harsh starlight, letting temperatures drop and simple molecules form and stick to grain surfaces as thin ices. These coated grains act like tiny chemistry labs, helping more complex molecules come together and allowing clouds to cool and collapse under gravity. In those sheltered cores, known as small dark globules, the collapse can eventually birth new stars. If you want a household comparison, dust in your attic hides a nest of forgotten things, and in space the dust hides the raw material for future suns and planets. Astronomers don't only look at visible light to study these clouds because they hide so much, they switch to longer wavelengths like infrared and radio that can slip through or pick up the dust's faint glow. Using those windows, telescopes can see the warm breath of the grains or the signatures of molecules frozen on them, revealing structure and motion inside the clouds. Practically speaking, interstellar dust matters. It changes how bright and how red distant objects appear, so researchers must correct for it to measure the true properties of stars and galaxies. It's like wiping a smudge off a camera lens, only the smudge is on a galactic scale, and sometimes it makes for prettier, spookier pictures than you expected. Bok globules, stellar nurseries cloaked in shadow. These small, dark clouds are pockets of cold gas and dust that block visible starlight, so they stand out as inky patches against the brighter backdrop of the sky. They hide their contents from ordinary telescopes because tiny solid grains scatter and absorb the light that our eyes, or optical cameras, would normally pick up. Astronomers use infrared and radio instruments to peer inside. Those wavelengths slip through the dust more easily, like warmth leaking through a blanket. Material inside is cold and dense compared with the surroundings, and gravity can slowly pull it together until a tiny, hot ball begins to form at the center. That beginning stage of a star is often cloaked so well that only the heat glow at longer wavelengths gives it away, which is why scientists say these clouds are stellar nurseries. They usually don't birth huge numbers of stars at once. Instead, a single cloud often forms one or a few stars, so think of them as a small family workshop rather than a factory. Everyday objects can help make the idea stick. A foggy bathroom mirror shows how moisture hides reflections, while a cluster of dust bunnies under a couch blocks light in the same way these clouds block starlight. Picture raisins in a loaf of bread, dark, dense bits scattered through a lighter dough. Only these raisins are cold grains that help glue gas together into a future sun. A little humor helps here. They're the universe's dust bunnies that actually do something useful, unlike the ones in your living room. External forces sometimes shape these clouds into comet-like silhouettes when a nearby bright star blasts them with radiation, or they can slowly evaporate away and disperse into the surrounding space. Observing how they change provides practical clues about how stars like our Sun get started and how small groups of stars form, information useful for comparing theory with real cases. Telescopes that sense heat and radio waves give current, direct evidence of hidden embryos of stars, so researchers combine those views to build a clearer picture of these shadowed nurseries. Molecular clouds, cradles of darkness. Cold, dark swathes of gas and dust in space are where new stars take shape. These clouds are mostly made of molecular hydrogen, two hydrogen atoms stuck together, plus helium and tiny solid grains we call dust. Temperatures inside drop to a few tens of degrees above absolute zero, so everything is extremely cold. Think of a freezer that never turns off. Densities are still far lower than the air in your home, but compared with the thin gas between stars they are crowded. A single cubic centimeter can hold from a few hundred up to about 1 million particles. Sizes range from a handful of light-years to regions that stretch across many tens or even hundreds of light-years, and some contain as much mass as thousands or millions of suns. Visible light from background stars is swallowed or scattered by the dust, which is why these regions look like black blotches against the Milky Way. Dust acts like heavy curtains for starlight. Telescopes that see in radio and infrared light can peer inside because dust and certain molecules glow at those wavelengths. Molecular hydrogen itself is shy. It doesn't give off the lines we can easily see at these cold temperatures, so astronomers often look for carbon monoxide instead, a molecule that speaks up loud and clear in radio waves and helps map the cloud's shape and motion. That trick is similar to looking for smoke to know where a hidden campfire is burning. Star formation inside these clouds starts when parts of the gas lose their balance and collapse under gravity. Tiny irregularities, supersonic whirls and shocks, a kind of interstellar turbulence, squeeze material into denser clumps. Magnetic fields thread the gas and can act like invisible rubber bands, resisting collapse or guiding flows of material. Most of the cloud's mass never becomes a star, only a small fraction ends up in the densest cores that form protostars. In practical terms, this means a giant cloud can spawn a whole cluster of stars while leaving most of its gas behind, like a baking tray with a few perfect cookies and lots of crumbs. You can picture a molecular cloud by comparing it to familiar things. A fog bank blocks distant lights, yet feels insubstantial if you wave your hand through it. The cloud is similar but vastly larger and colder. Dust grains are like tiny soot particles that both hide and help. They shield molecules from harsh starlight and provide surfaces where simple chemical reactions happen. Hydrogen sticking to a grain surface is a key step toward forming more complex molecules. And yes, the chemistry can be oddly homely. Astronomers find common molecules such as water, ammonia and simple organic compounds in these cold pockets, though spread out far more thinly than in your kitchen. Observations show that molecular clouds are not peaceful, static objects. They live dynamic lives, changing under the influence of neighboring stars, supernova shockwaves, and internal motions. Newborn massive stars blast away gas with ultraviolet light and winds, carving cavities and sometimes triggering fresh rounds of collapse nearby. The overall picture is one of delicate balance between gravity trying to pull gas together and several opposing forces that push back. In short, molecular clouds are the universe's dim, dusty nurseries, quiet and cold, but full of motion, chemistry, and the slow, patient work of building stars. Dark galaxies, invisible cities of matter. Some galaxies are made almost entirely of gas and the invisible mass that tugs on it, yet they give off almost no starlight. Astronomers find them not by the glow of stars but by the faint radio whisper from neutral hydrogen, a particular radio signal at a wavelength often called the 21 centimeter line. Radio surveys that map hydrogen across the sky pick out blobs of gas where optical telescopes see nothing or only a ghostly smudge. Think of it like finding a city by its water towers rather than its streetlights. One well-known candidate shows up as a big patch of hydrogen moving in a way that suggests a massive unseen halo is holding it together. Some of these objects have names used in radio catalogs, and a few have been called almost dark, because deep optical images eventually reveal a handful of very faint stars. Others remain stubbornly invisible in visible light, so astronomers debate whether they are true dark galaxies or simply tidal debris, streams of gas torn off during close encounters between ordinary galaxies. In plain terms, the difference is between a ghost town that has always been empty and a pile of rubble left after a wreck. There are a few plausible explanations for why stars don't form in these places. The gas might be too spread out to clump into dense pockets where stars can ignite. External forces like radiation or past collisions can heat the gas, keeping it from cooling and collapsing. Another factor is metallicity, the amount of heavier elements in the gas. Low metallicity makes it harder for the gas to radiate away heat and settle into star-forming clouds. A simple everyday analogy: damp wood won't catch fire easily no matter how much wood you pile up, if you never get a spark and the wood is too wet to smolder. Studying these dim objects matters because they act as test cases for how galaxies start and fail. If dark galaxies are common, they would be hiding lots of ordinary matter that we miss in optical surveys, and they would show where dark matter can collect gas without making stars. Observationally, this is tricky. Radio telescopes are excellent at finding the hydrogen, but follow-up with very deep optical imaging or spectroscopy is needed to confirm whether there really are no stars at all. It's like using a metal detector to find a buried box and then digging carefully to see if it contains coins or just a rock. Practical tools and strategies have changed the hunt. Astronomers combine wide-area radio maps with targeted deep optical exposures and simulations that model how gas behaves inside dark matter halos. Sometimes an object that looked like a promising dark galaxy turns out, after closer inspection, to be a faint, low-surface brightness dwarf with a few elderly stars, still interesting, but not the cosmic ghost town some hoped for. The whole process often feels like a cosmic game of hide-and-seek, and researchers are learning to be patient. Signals are faint and the universe is full of deceptive shapes. A little humor helps. Searching for dark galaxies is a bit like going on a ghost tour where the only sign of life is the echo of your own footsteps. But the echoes are informative. Every candidate teaches us about the conditions needed for star formation, about how interaction and environment can snuff out the light, and about where matter prefers to hide. The mysteries remaining are real, and that makes the hunt exciting. There are invisible cities out there, and astronomers are slowly mapping their streets. Dark matter halos, the cosmic skeleton. Galaxies sit inside vast, invisible clouds of extra mass that dominate their gravity and shape how they move. This hidden stuff, which we call dark matter, doesn't glow or block light the way stars and gas do, but it makes up most of the weight of a galaxy system, often several times more mass than all the stars combined. That means when you look at a spiral galaxy, the bright disk you see is only the tip of the iceberg. An extended, mostly spherical envelope surrounds it and holds the whole system together. Astronomers infer these envelopes from how objects actually move. Stars far from the galactic center zip around almost as fast as stars much closer in, whereas without extra mass they should slow down. Light itself sometimes gets bent as it passes near massive galaxies, producing subtle distortions or even arcs. That bending betrays more mass than meets the eye. Watching small companion galaxies orbit a larger one also gives clues. Their motions act like test particles tracing the invisible mass. Think of it like watching leaves whirl around an unseen storm. The pattern tells you where the winds are strongest. The structure of these halos is not perfectly smooth. Computer models that simulate gravity show that halos contain many smaller clumps inside them, and observations find faint satellite galaxies occupying some of those clumps. In everyday terms, picture a big sponge with raisins scattered throughout, where the sponge is the halo and the raisins are tiny galaxies. When two galaxies collide, their halos merge first, wrapping and tugging on each other long before the bright stars even touch. That merging history helps explain why big galaxies live in crowded neighborhoods while more isolated ones remain small and quiet. Understanding these invisible envelopes matters for predicting where galaxies form and how they evolve. Telescopes that map mass through light bending or that track motions of satellite galaxies rely on models of halo shape and size to interpret what they see. Some things still puzzle researchers. The exact number and distribution of small clumps inside halos sometimes differ between models and observations, and that keeps scientists testing ideas about what dark matter actually is. Meanwhile, for anyone who likes metaphors, halos are the cosmic scaffold, awkward to hug and impossible to photograph, but absolutely essential if you want the universe to keep its shape. Machos and wimps, candidates for the invisible. Some of the simplest ideas for the universe's hidden mass involve things that are just hard to see rather than truly invisible. One category is made up of dim, compact objects, faint stars, burnt-out star-like bodies, free-floating planets, and black holes that don't give off light. Another idea is a new kind of tiny particle that hardly ever interacts with normal matter, slipping through ordinary detectors like a ghost at a crowded party. Both ideas try to explain why galaxies act as if there is much more mass present than we can see. Objects that barely shine are often called machos in technical talk, but you can think of them as the universe's stealth stones. Examples include objects that never ignited as bright stars, or planets wandering between systems. When one passes in front of a background star, its gravity can act like a magnifying glass, making that star briefly brighten. This effect is easy to picture as someone moving a lens in front of a flashlight. Telescopes watch many stars to catch these fleeting brightening events, and astronomers use those signals to count how many stealthy bodies might be hiding in galactic halos. The results from those searches show that while such hidden objects exist, they probably don't add up to all of the missing mass. In everyday terms, finding a few hidden rocks in a field doesn't explain why the whole field feels unusually heavy. On the other hand, the particle idea imagines dark matter as a legion of tiny, nearly non-interacting bits of matter. These hypothetical particles are often called WIMPs in shorthand, which hints that they interact only rarely with normal particles. Think of them like extremely shy mosquitoes that fly through a room without ever touching a person. Because they pass through ordinary matter so easily, detecting them requires extreme patience and clever tricks. One method is to build very quiet detectors deep underground where the noise from cosmic rays and other disturbances is greatly reduced. In those silent environments, scientists hope to feel the tiny kick when a dark particle finally bumps an atom. Another route is to look for byproducts of dark particles colliding with each other high in space, faint flashes or unusual particles that telescopes and detectors could spot. Particle accelerators try a third tack by smashing known particles together at high energies to see if new, invisible particles are produced and inferred from missing energy. Comparing the two, a key difference is provenance. The dim object idea uses ordinary matter in strange places, while the particle idea requires something new that doesn't behave like any normal material. Observations of how galaxies rotate and how large structures form tend to fit better with a smoothly distributed particle component rather than clumps of ordinary dark objects. That said, the quest isn't over. Detecting a WIMP would be like discovering a secret ingredient in a recipe that finally explains why the cake rose. Finding a population of machos that account for a large fraction of the missing mass would be more like stumbling on a drawer full of heavy rocks under the floorboards. Both paths demand patient, careful work, and a sense of humor helps. Scientists lower detectors into deep mines, stare at countless starlight curves, and sift through mountains of data hoping to catch a rare wink from the dark side of the universe. It's a hunt for hidden guests at a cosmic party. Some are big and quiet, like introverted boulders, and others so tiny and polite they almost never touch anyone. Either way, knowing which kind of invisible is out there would change how we understand the world, and give astronomers one more good line for complaining about their missing socks. Axions and sterile neutrinos, particle suspects. Two very different kinds of hypothetical particles have been put forward to explain the universe's missing mass. One behaves like a whispering field, the other like an extremely shy particle. Axions are thought to be incredibly light and neutral. They barely interact with ordinary matter and could form a smooth background that fills galaxies. Sterile neutrinos, by contrast, would be a new kind of neutrino that does not take part in the usual forces we know, hiding from detectors except through gravity or by slightly mixing with the familiar neutrinos. Both are serious candidates because they naturally slip past the usual ways we try to see stuff, yet still tug on stars and galaxies through gravity. Axions can be pictured as a faint radio signal spread across space. Under the right conditions, for example inside a very strong magnetic field, an axion can turn into a tiny amount of microwave radiation, and experiments listen for that whisper. ADMX is one example of a setup that uses strong magnets and sensitive microwave receivers to try and pick up such a conversion, much like tuning a radio to find a weak station under static. Stars also act as laboratories. If axions exist, they would carry energy away from a star's core, subtly changing how the star cools. Astrophysicists use that stellar behavior as a practical constraint, a kind of cosmic thermometer to test theories. Light shining through walls experiments are another clever idea. Send photons toward a wall in a magnetic field, and if axions are real, some photons could briefly become axions, pass through, and then reappear as photons on the other side. A neat idea that sounds like magic but is straightforward in principle. Sterile neutrinos are more like wallflowers at a party who never dance, but sometimes leave a telltale footprint. Ordinary neutrinos are already famous for barely interacting, but they do take part in the weak force. Sterile neutrinos would refuse even that, interacting only through their mass and by occasionally swapping identity with ordinary neutrinos. That swap, called mixing, can be explained simply as two flavors of soup being stirred together so that spoonfuls taken out are mixtures. The spoonful analog here is an ordinary neutrino that sometimes appears to be a sterile one. If sterile neutrinos have enough mass, they could slowly decay and produce faint 10th-ray light, so 10th-ray telescopes scan galaxy clusters and the Milky Way for narrow, unexplained lines that might be the smoking gun of such decays. The search is like standing in a dark room with a flashlight and looking for a single unexpected glint. Comparing them helps to see why experiments are so different. Axions act like a coherent wave, more of a field than discrete particles in some regimes, and so experiments use resonant cavities and magnets to pick up an oscillating electromagnetic signal. Sterile neutrinos behave more like ordinary particles that can be counted and whose decays produce sharp flashes of energy detectable by telescopes. Think of the difference as ocean swell versus a school of minnows. One produces smooth, rhythmic motion, the other individual darts that can be counted. Both approaches are complementary, and both face practical hurdles: background noise, tiny signals, and the need to cover many possibilities, which keeps experimentalists inventive and sometimes a bit caffeinated. Real-world analogies make the search feel less abstract. Tuning an axion experiment is like adjusting a radio's frequency while trying to hear a distant station through city static. Patience and fine control matter. Hunting sterile neutrinos with 10th-ray satellites is like trying to spot a single firefly in a field by monitoring for a flash at a very specific color. A positive detection would be a huge discovery, not just answering a big cosmic question, but opening a door to new physics and new technologies down the line, though the immediate reward might just be bragging rights at conferences. Either way, the chase blends clever laboratory tricks, astronomical sleuthing, and a dash of creativity, and that makes the search for axions and sterile neutrinos strangely fun, even if the particles themselves prefer to remain invisible. Cosmic voids, the universe's darkest regions. Most of the universe's volume is taken up by enormous, almost empty spaces where galaxies are scarce and matter is thinly spread. These areas, called voids by astronomers, are not literal nothingness but places where there are very few galaxies compared with the busy filaments and clusters that make up the cosmic web. Think of a city map. Neighborhoods full of houses and parks show up as dense clumps, while the large industrial zones or unused fields stand out as gaps. Voids are the cosmic equivalent of those empty lots, just a lot bigger and colder. Voids can be incredibly large, often stretching across tens to hundreds of millions of light-years, so big that you could fit many galaxy clusters inside one and still have room for a picnic. They are underdense, meaning they contain far less matter than the average region of space. A handful of small, faint galaxies may live there, along with thin gas and invisible dark matter. That sparse population is like finding a few stray houses on a long, empty highway instead of a bustling suburb. Because there is less material inside voids, things inside them evolve more slowly and simply, which makes them useful places for scientists to study the basic rules of the universe. These regions form because small differences in the early distribution of matter grow over time. Denser parts pull in more material and become the crowded nodes and filaments, while the emptier parts lose material and expand. Picture bread dough rising around pockets of air, or bubbles in boiling water. The bubbly parts grow and the dough around them thins out. In cosmic terms, gravity moves matter away from void centers into the surrounding structure, so the voids become emptier and larger with time. Because of this dynamic, voids expand a bit faster than the average expansion of the universe, and that makes them sensitive indicators of how expansion and gravity behave on large scales. Astronomers find voids by making three-dimensional maps of where galaxies are located, using telescopes that measure distance as well as direction. It's similar to mapping every streetlight in a town and then spotting the stretches where there are none. Once identified, voids provide a cleaner laboratory for testing ideas about how the universe works. With fewer confusing interactions, subtle effects stand out more clearly. For example, light traveling through a void can get slightly altered in energy, leaving faint imprints that experts study to learn about the universe's expansion and the way gravity acts across vast emptiness. It's like sending a signal down an empty hallway versus a crowded market. The message changes less in the quiet corridor. Despite the name, voids are not perfect vacuums. Pockets of gas, a smattering of dwarf galaxies, and invisible dark matter still thread through them, but at much lower density. These lonely galaxies are like isolated farmhouses in a desert. They survive but live under different conditions than their city-dwelling cousins. Studying such inhabitants helps scientists understand how environment shapes galaxy growth. For instance, galaxies in voids often have more gas relative to stars and can form stars differently than those in denser clusters. That contrast gives a practical handle on the role surroundings play in shaping cosmic objects. As sky surveys and instruments get more detailed, maps of the cosmic web and its voids keep improving, revealing finer structure and more subtle phenomena. New data allow researchers to compare observations with theoretical models, checking whether our understanding of gravity, dark energy, and matter holds up in the universe's quietest neighborhoods. In short, these dark regions are not mere empty backdrops. They are active testing grounds where the simplicity of emptiness helps reveal the universe's complicated rules, and occasionally gives astronomers a cosmic joke about how even the universe needs its own quiet zones. The cosmic microwave background cold spots. Astronomers studying the faint afterglow left over from the very early universe have found tiny patches that are a bit cooler than the surrounding sky. This afterglow is like the last warmth from a big cosmic oven, now stretched into microwaves that we can map across the whole sky. The temperature differences are incredibly small, measured in millionths of a degree, yet they show patterns that tell us about how the universe behaved when it was still very young. Think of it as a vast, subtle fingerprint written in temperature instead of ink. One of those cooler patches is noticeably larger and darker than the usual ripples, and it sticks out on full sky maps made by different telescopes. Some researchers argue that this feature could just be an unlikely but natural fluctuation, like getting a long stretch of one face when you flip a fair coin many times. Others point to a different, more physical possibility, a huge region with fewer galaxies than average, known as a supervoid, lying in the same direction. Light that crosses such an emptier region can lose a bit of energy, producing a slightly cooler signal on our maps. A useful everyday picture is sunlight dimmed and cooled as it passes through a thin, chilly fog. Other explanations get more adventurous and a little stranger. A few ideas suggest that the cold patch might be a sign of unusual events or features in the early universe, things that would be like a knot or wrinkle in the fabric of spacetime. These suggestions are speculative, and scientists treat them with caution. Still, they are useful because they push observers to devise clever tests, which in turn sharpen our understanding. After all, science advances when strange clues force better detective work. A playful way to think about it is like hearing a mysterious rattle in an engine. First you check the easy things, and then you consider bizarre possibilities, like a loose garden gnome, before fixing the problem. To sort among these options, teams compare detailed sky maps with surveys that count galaxies in the same directions, run computer simulations, and look for subtle patterns that match one idea or another. Multiple independent measurements help reduce the chance that the cold patch is a trick of noise or equipment. In practical terms, the cold patch is a useful test. It helps validate our theories and pushes instruments to be more precise. It may remain a quirky cosmic wrinkle, or it might point to something deeper. Either way, it keeps astronomers busy and a little amused, like detectives arguing over a clue that could be either a smudge or a masterpiece. Gravitational waves, hearing the dark collisions. Ripples travel outward when something heavy moves suddenly, and gravitational waves are those ripples in the fabric that ties space and time together. Think of that fabric as a stretchy sheet. When two very heavy objects whirl into each other, they tug and slap the sheet, sending waves that race across the universe. These waves carry information about the crash, how heavy the objects were, how fast they spun, and how violent the final smash was. They pass almost untouched through gas, dust, and stars, so they bring a clean report from deep inside places we cannot see with ordinary telescopes. Detecting those tiny wiggles requires instruments that are a bit like very fancy tape measures. A laser beam is split and sent down two long, perpendicular tunnels, bounces off mirrors, and comes back to meet itself. If a gravitational wave stretches one tunnel and squeezes the other even a tiny bit, the two light beams arrive out of sync and the pattern of light changes. The shifts are far smaller than anything you can feel, smaller than the atoms in the mirror coatings, in fact, which makes the whole setup feel like trying to hear a pin drop inside a cathedral during a fireworks show. It is delicate work, and engineers spend a lot of time keeping the mirrors perfectly still, not an easy job when earthquakes, passing trucks, and thermal jitter all want to chip in. Listening to the shape of a wave is like hearing the notes of a crash. A slow, deep rumble suggests two very heavy objects, a quick, rising chirp means two denser, faster dancers spiraling inward. By turning the signal into sound we can literally listen to these events, and the way the pitch climbs tells scientists how the orbit changed as the objects closed in. Combining signals from several detectors lets researchers figure out where in the sky the sound came from, in the same way that two ears help you locate a chirping bird, more ears give a better idea of direction. Gravitational wave measurements open a window on things that emit almost no light at all. Black holes, for instance, are invisible to cameras but make very loud gravitational music when they collide. Neutron stars, which are like city-sized balls of extreme stuff, can also sing in ways that reveal how stiff or squishy their insides are. These signals test our ideas about gravity by checking if the waves behave as expected while crossing vast reaches of space. There's also a human side. Turning faint spacetime ripples into audio clips makes the cosmos feel oddly domesticated, like putting the universe on your playlist, and yes, some of those clips sound more like chirps than chart-topping hits, but they're priceless to scientists and oddly satisfying to listen to. Black hole mergers, fireworks in the dark. When two black holes draw near each other they fall into a tightening dance, circling faster and faster until they finally crash together and become one. A black hole itself is a place where gravity is so strong that not even light can escape, so when two of these objects meet the event is dramatic but usually invisible in ordinary light. The motion sends out ripples in space itself, and those ripples are the key signature that tells astronomers a merger has happened. Think of it as two whirlpools in a bathtub merging into one big, angry swirl. The water sloshes differently and you can feel the change even if you can't see below the surface. These ripples are called gravitational waves, and they behave like the waves you make when you toss a stone into a pond, except the pond is space and the stone is enormous. Instruments on Earth can pick up these tiny wiggles, translating them into data that often looks like a rising tone or chirp. That chirp grows higher and faster as the black holes close in, similar to the way a speeding car's engine pitch changes when it races past. It is a brief event, often over in a fraction of the time it takes to boil an egg, but packed with intense motion and energy. Most mergers happen in darkness because there is no gas or light to shine, so they are true fireworks you can't see with your eyes. Sometimes, though, if the black holes are surrounded by gas or stars, the collision can stir up matter and produce flashes or jets that do shine, rather like a car hitting a dusty sign and kicking up a cloud. Scientists use these hidden explosions to measure things that would otherwise be impossible to weigh, such as how massive the black holes were before they joined and how fast the new one spins. The spin is easy to grasp. Imagine a figure skater pulling in their arms to twirl faster. Black holes behave in a similar way when their material rearranges. Listening to these cosmic crashes teaches us about gravity in a way that ordinary telescopes cannot. By comparing the shape of the chirp to predictions, researchers test how well our ideas about gravity hold up under extreme conditions. Practical benefits follow too. Knowing where mergers happen helps map the population of black holes across the universe and hints at how stars and galaxies evolve. And yes, the whole idea is a little funny. Space throws a fireworks show that doesn't light up the sky, but instead makes the very fabric of spacetime hum, like a silent drumbeat you can feel if you have the right ears. Tidal disruption events, stars torn apart. When a star wanders too close to a giant black hole, the pull on the side nearer the hole becomes much stronger than the pull on the far side, and the star is stretched until it breaks apart. This pulling difference is called a tidal force, which you can think of like the moon tugging on Earth's oceans but turned up to cosmic extremes. At a certain breakup distance, often called the tidal radius, the star can be ripped into a long stream of gas and dust, and that sudden shredding lights up the surroundings. The shredded star doesn't just disappear quietly. Part of the torn material flies outward, while a lot of it falls back toward the black hole and settles into a spinning, flattened whirlpool of hot gas known as an accretion disk. Imagine spilling a bowl of spaghetti into a drain. Some strands swirl in and heat up as they spiral down. The friction and compression in that disk turn orbital energy into heat and high-energy light, producing a bright flare that telescopes can spot across vast distances. These flares often shine in ultraviolet and 10th rays, and sometimes we see radio signals too if powerful jets are launched. Astronomers detect these dramatic events by watching for sudden brightening in the centers of galaxies and then following the changes over time. Surveys that scan large swaths of the sky are especially good at catching them, because the events are unpredictable and short-lived on cosmic timescales. The light from a tidal disruption event typically rises and then fades over weeks to months as the supply of falling debris dwindles, and the color and spectrum of that light tell scientists about temperature, composition, and how matter behaves under extreme gravity. Not every black hole produces this kind of fireworks. Very small black holes are unlikely to catch stars, and extremely massive ones can swallow a star whole before it has a chance to be torn apart outside the point of no return. So tidal shredding tends to happen around black holes in a certain mass range where the breakup takes place outside the event horizon. Studying these events gives a practical way to weigh black holes and probe their feeding habits, data that helps answer questions about how galaxies grow and how matter behaves in the strongest gravity we can observe. There are surprising bits of everyday analogy that help make sense of the chaos. Think of the star as a marshmallow near a powerful hair dryer. It softens, stretches, and eventually flattens, with bits blown away. Or picture a cat being pulled from both ends by two curious toddlers. Before you know it, the cat is a long story, and everyone learns a lesson. Slightly less cute, but more useful, tidal disruption events let astronomers test models and run computer simulations that mimic the taffy-like stretching, the formation of the spinning disk, and sometimes the launching of fast jets, cosmic garden hoses blasting particles outward. A little humor helps. The universe has a messy appetite, but these cosmic meals are real tools for learning about extreme physics and the hidden giants at galactic centers. Ultra-compact dwarfs and faint fuzzies. Astronomers studying crowded galaxy clusters noticed unusually bright, compact clumps of stars that stood out like tiny streetlights in a fog. These objects are brighter and denser than typical star clusters, yet much smaller and dimmer than full-blown galaxies. They often sit in places like the Fornax and Virgo clusters where galaxies crowd together. Think of them as the apartment high-rises of the stellar world, a lot of stars packed into a modest footprint, shining more intensely than their neighbors. One idea for how these compact clumps formed is simple and vivid. A bigger galaxy can get its outer layers torn away by gravity during close encounters, leaving behind a dense central core. This leftover core can look like a supersized star cluster, and it may still carry the heavy elements and a central black hole from its former glory. Another possibility is that some of them are the most massive cousins of normal star clusters, born that way in extreme bursts of star formation. Either way, they can weigh as much as millions of suns, and proving their origin often depends on measuring how fast the stars inside are moving. There is another, quite different class of objects that are easy to miss unless you know where to look: soft, extended star clusters that sit peacefully in the flat disks of some galaxies. Observers calling them faint fuzzies found them in galaxies like NGC 1023. They have a low surface brightness, which means their light is spread out and they look faint against the background. Picture a handful of dandelion heads scattered across a lawn at dusk, subtle, spread out, and not trying too hard to be noticed. These clusters are often old and metal-rich, and they tend to orbit in disk-like patterns rather than in the more random, halo-like orbits of typical globular clusters. Finding and studying both types requires sharp eyes and clever tools. Telescopes with excellent resolution, including space telescopes and big ground-based instruments, are used to take images where size and shape can be measured. Spectroscopy, splitting the light into colors, lets astronomers measure the speed of stars inside the object, which reveals mass, and check the chemical fingerprints to learn about composition. It's a bit like using a magnifying glass and a speed gun at the same time. You measure how big the crowd is and how frenzied their motion is. Why care about these obscure-sounding objects? They are compact archives of a galaxy's violent past and peaceful outskirts. The dense, skyscraper-like clusters can hide clues about black holes and violent interactions that stripped galaxies down to their cores. The faint, spread-out clusters teach us about how disks form and how star formation can proceed gently over long times. Both act as living fossils that help piece together the life stories of galaxies, and studying them is one of astronomy's ways of reading a cosmic neighborhood watch log. Plus, they make astronomers smile, because nature sometimes prefers tiny, unexpected characters to steal the show. Low surface brightness galaxies, ghostly giants. These galaxies glow so faintly that their light is spread thin, like candlelight viewed through a foggy window. Surface brightness describes how much light falls on a patch of sky, and in these systems that amount is very low. The same total number of stars can look much dimmer when they are spread out over a huge area. Think of sprinkling a handful of fairy lights across a stadium versus clustering them on a small table. The table looks bright, the stadium looks ghostly. Telescopes need long exposures and careful image processing to pull them out from the background glow of the night sky. Stars in these galaxies tend to be sparsely arranged, and the usual bright, short-lived blue stars are rare because new star formation is slow. That means the visible light is often dominated by older, cooler stars, so colors look muted. At the same time, there is often a lot of cold gas, raw material for making stars, that somehow hasn't turned into many new suns. In plain terms, lots of fuel but not a lot of engines running. This low activity makes them appear both ancient and sleepy, and sometimes oddly elegant, like a living room with plenty of furniture but no one home. What holds them together is frequently something you can't see directly, a large amount of unseen mass. Astronomers call this dark matter, which behaves like extra weight in the galaxy without shining. You can compare it to an iceberg. The small tip you see is the starlight, while the massive hidden bulk underneath is the dark matter, keeping the system from flying apart. Measurements of how stars orbit inside these galaxies show much more gravitational pull than the stars themselves can account for, giving them very high mass-to-light ratios. That makes them excellent laboratories for testing ideas about how dark matter works. Sizes vary wildly. Some are modest, dwarf-like smudges barely noticeable, while others are truly vast, with disks that stretch far beyond what you would expect for such dim light levels. A few famous examples are faint but enormous, and they reveal spiral arms and structures that only become clear when images are pushed to reveal the faintest details. Detecting these features is a bit like using a long-exposure camera to reveal the trails of slow-moving fireflies across a field. Their existence matters for understanding how galaxies form and evolve. Standard models that explain bright galaxies don't always predict why some systems keep plenty of gas but make so few stars, or how such diffuse disks remain stable. Finding and studying these ghostly giants forces scientists to refine theories about gas cooling, star formation thresholds, and the role of environment. Amateur astronomers can even pitch in by stacking many long-exposure images to bring out faint edges, which is a fun way to feel like a cosmic detective. After all, facing a galaxy that barely lights up the sky is humbling, and a little like trying to read a book by moonlight while wearing sunglasses. Interstellar dust grains, tiny absorbers of light. Interstellar space is not completely empty, it contains tiny solid particles that grab and scatter starlight, changing how we see the galaxy. These grains are extremely small, from a few nanometers up to a fraction of a micrometer, so tiny that a single grain is comparable to smoke particles or a fine speck of soot. Composed mostly of rocky bits like silicates and carbon-rich material, and sometimes coated with frozen gases in the coldest places, they act like miniature dust bunnies drifting between the stars. Light hitting them can be absorbed or bounced away, and because shorter, bluer, wavelengths are scattered more easily than longer, redder ones, distant stars often appear reddened, much as a campfire smoke can make the sun look red at dusk. They do more than just block light. On the surface of these particles chemistry happens. Individual hydrogen atoms stick to a grain, meet another hydrogen, and leave as a molecule. This surface chemistry is one of the main ways molecular hydrogen, the simplest and most common molecule in space, forms. Grains also influence temperature. When ultraviolet light strikes a grain, it can knock off an electron. That escaping electron transfers energy to surrounding gas and helps heat it. In short, these specks help shape the physical conditions where new stars and planets later form. Astronomers spot their handiwork in several ways. Dark clouds that hide background stars mark regions where dust is dense enough to block visible light. Instruments sensitive to infrared detect the faint warmth re-emitted by dust after it absorbs starlight, revealing structures invisible to optical telescopes. Measurements of how much starlight is dimmed and how the color shifts allows scientists to infer grain size and composition. Polarized starlight offers another clue. Elongated grains tend to align with magnetic fields, and that alignment causes light waves to prefer one direction, much like polarized sunglasses cut glare on a lake. Think of household dust floating in a sunbeam. The same basic idea applies on a cosmic scale, only with grains made of rock, carbon, and ice, and spread across light years. They quietly remove elements from the gas by locking them into solid form, affect how clouds collapse to form stars, and provide the raw surfaces for important chemical reactions. A little humor helps here. These cosmic dust grains are the universe's tiny vacuum cleaners, only they're better at chemistry and worse at obeying instructions. The role of dust in hiding star formation. Interstellar dust grains are tiny solid particles that soak up and scatter starlight, and because they block blue and ultraviolet light most effectively, dusty regions can look dark or reddened in visible images. These grains are extremely small, typically about 1/10 of a micrometer across, and are made of simple stuff like silicate minerals, carbon compounds, and frozen water or other ices on their surfaces. Think of them like microscopic soot and sand that floats between the stars. When light from baby stars tries to get out, the dust either sends it off in a different direction or gobbles it up. The result is that whole stellar nurseries can be hidden from ordinary telescopes, much like a fog bank hides a harbor. Newborn stars are often born deep inside thick, dusty clouds, so their bright ultraviolet and visible light never escape directly. Instead, dust warms up and then shines at longer wavelengths, infrared and sub-millimeter light, which human eyes cannot see but special telescopes can. Instruments that work at those wavelengths, such as space-based infrared observatories or ground arrays that detect millimeter waves, act like night vision goggles for astronomers. They reveal the hidden heat glow of forming stars and the cold clouds around them. It is similar to how a hot road in summer doesn't look bright to your eyes but you can feel the heat. Telescopes that feel the infrared can find stars the eyes miss. Dust does more than just hide things, it actually helps star formation happen. By blocking energetic light, dust shields the gas inside clouds and lets it cool, and cooler gas can collapse under its own gravity to make stars. Tiny dust grains also provide surfaces where simple molecules, especially hydrogen, can meet and stick together more easily, acting like microscopic sticky notes that bring partners together. This makes dust a partner in crime and in creation. It hides the action but also creates the conditions for that action to occur. For astronomers trying to measure how many stars form in a galaxy, dust is a practical headache. Relying only on visible light gives an underestimate because the most vigorous star-forming regions are often the most dust-enshrouded. So scientists combine observations across the spectrum, ultraviolet to catch unobscured young stars, infrared to see the dust's glow, and radio or millimeter waves to trace the cold gas itself. A simple everyday comparison is counting candles in a smoky room. If you only count visible flames you miss the candles smoldering behind curtains, but if you also measure heat or smell you get a better total. Dust can also be a useful detective tool. Aligned dust grains can polarize light, giving clues about magnetic fields threading the clouds, and different molecules frozen on grains emit characteristic signals that help identify chemical conditions. In effect, dust both hides and tells a story, so learning to read its signals is crucial for a true picture of star birth. And yes, dust is annoying, both in your house and in the galaxy, but without it, many of the universe's most dramatic light shows would never get started. Observing the dark, infrared, radio, and 10th rays. Light our eyes can't see carries stories about the darkest, most hidden places in the universe, and astronomers read those stories in infrared, radio, and 10th rays. Infrared light is like a warm glow coming from dust and cool objects. It slips through dusty clouds that block visible light, revealing newborn stars still wrapped in their dusty blankets. Radio waves trace enormous clouds of gas, whispering the structure of galaxies and the long, booming jets launched by hungry black holes. 10th rays come from extreme environments where gas is super hot or particles slam into magnetic fields, so they mark collisions, shock fronts, and the immediate neighborhoods of black holes and neutron stars. Telescopes that study these bands need special tricks. Infrared detectors must be kept very cold so their own heat doesn't swamp the faint cosmic glow. Think of them as ice cream that can't melt. Radio telescopes can be huge dishes or networks of many dishes working together to act like one giant ear. This trick, called interferometry, sharpens the view by combining signals from widely spaced antennas. 10th ray telescopes use mirrors arranged at shallow angles so the high-energy photons glance off instead of crashing straight into the instrument, which is a bit like skipping stones across a pond. Some of these instruments live in space, while others sit on high, dry mountaintops to avoid the interference and absorption caused by Earth's atmosphere. Everyday technology gives good analogies for how these observations work. A TV remote uses infrared to talk to your set. Similarly, celestial infrared tells astronomers about heat and hidden structure. Your car radio picks up music over broad areas, and radio telescopes pick up signals from enormous regions of space that can span whole galaxies. Medical 10th rays image dense bones by using high-energy light that passes through flesh differently than bone, just as astronomical 10th rays highlight very energetic material that ordinary light misses. These familiar examples help make sense of why astronomers pick one type of light over another when they want to study a particular problem. There are real challenges to getting the data, and dealing with them takes creativity. Human-made radio noise from cell towers and satellites can clutter radio observations, so observatories often sit inside radio-quiet zones, quiet as a library, but for aliens. Infrared detectors require cooling systems and careful thermal shielding, because even the telescope itself can produce infrared that interferes with the faint cosmic signals. 10th ray instruments must handle particles that would melt ordinary electronics, meaning they need specialized shielding and clever data filters. After collecting the photons, scientists still have to process the signals into images and spectra, often assigning visible colors to invisible light to highlight different temperatures or chemical fingerprints. Pretty pictures, yes, but each color also encodes real physical information. A little patience, and a lot of engineering, turns these hard-to-see messengers into clear clues about the darkest objects in the universe. Simulations and virtual universes of darkness. Computer models let researchers build virtual universes where unseen stuff, like dark matter and the regions around black holes, can be watched and tested under controlled conditions. These models break space into many pieces or represent matter as lots of individual points that tug on each other through gravity, and they add gas and magnetic effects as needed. Think of it as a very detailed video game level where gravity is turned up and the rules are a bit stranger. In everyday terms, n-body simulations treat masses like marbles rolling on a warped trampoline, while gas in those simulations behaves more like water flowing down a drain. The same basic tricks that meteorologists use to forecast weather get reused to follow how gas cools, heats, and forms stars in a virtual cosmos. That approach lets scientists watch how invisible scaffolding, the dark matter web, shapes where galaxies land, much as the layout of roads shapes how a city grows. Black hole neighborhoods are handled a little differently and require extra care because gravity becomes extreme there. Researchers use codes that simulate both the hot, magnetized gas that swirls into a black hole and how light would bend and twist near it, so the predicted image can be compared with what real telescopes see. The Event Horizon Telescope, for example, relied on such simulated images to interpret the bright ring and dark center it observed, helping to test the basic picture of a shadow cast by a compact object. Short bursts of intense physics are modeled as if they were weather fronts, turbulent and messy, but the simulations let scientists isolate the role of magnetic fields that can launch jets, which are sometimes observed blasting out from galaxy centers. Virtual universes of darkness are also useful for testing ideas about the invisible matter that holds galaxies together. When a simulation places an invisible halo around a galaxy, that halo acts like a hidden scaffolding, and the simulated galaxy then responds by forming spiral arms, bulges, or staying small and faint. A concrete example is how simulations can show whether adding strong feedback, the energetic push from exploding stars or feeding black holes, prevents small galaxies from overgrowing, which helps match the simulations to real galaxy surveys. The comparisons are practical. Survey maps of galaxy positions and motions are pitted against many simulated universes to see which assumptions about the invisible stuff best match the real sky. There are limits, of course, and they matter. Simulations simplify some microphysics because fully resolving every tiny process would require impossible computing power, so researchers choose which details to keep and which to smooth over. It's a lot like rendering a distant crowd in a video game by using a few representative figures instead of drawing every face. Running these virtual universes takes large computers and clever tricks to split the work, often using graphics processors similar to those in gaming rigs. The payoff is practical. Simulations guide telescope designs, help prioritize observations, and even enable public virtual reality tours that let people fly through a dark matter web for outreach. And yes, there is a bit of joy in debugging the universe on a screen. You tweak a parameter, press run, and watch galaxies argue about who gets the most stars. The search for dark objects, surveys and missions. Large sky surveys and targeted space missions work together to find objects that give off little or no light, using clever tricks rather than relying on brightness alone. One common trick is to watch how visible stars and galaxies behave. If a star wobbles or a distant galaxy appears slightly stretched, that can point to unseen mass nearby. Surveys map huge swaths of the sky repeatedly, building a movie of changes and motions. From those movies scientists can spot the fingerprints of dark objects. This is similar to watching leaves on a pond to learn about an invisible fish below the surface. The leaves don't show the fish, but their ripples do. Microlensing surveys look for a brief brightening of a background star when a compact, dark object passes in front of it and acts like a temporary magnifying glass. Projects that monitor millions of stars search for those tiny blips. When one appears, follow-up observations can reveal whether the lens was a faint star, a free-floating planet, or something more exotic. Another method measures the precise positions and speeds of stars. Space missions that track stellar motion can reveal an unseen companion tugging on a star, much like noticing your neighbor's curtains sway and concluding someone walked past even if you didn't see them. That technique has turned whole catalogs of star motions into treasure maps for hidden masses. Gravitational waves give a very different kind of clue. They are ripples in spacetime produced when massive, compact objects like black holes collide. Ground-based observatories act like giant ears that listen for those faint chirps, and when a signal is detected it can tell us about the masses and behavior of objects that emitted no light at all. Meanwhile, arrays of radio dishes can combine their observations to image the shadow of a black hole, turning what was once purely theoretical into a visible silhouette. 10th ray and radio telescopes are still important because many dark objects betray themselves by how they affect nearby gas, heating it and making it glow in high-energy light. If no glow is present, that lack of light can itself be informative. Modern surveys produce oceans of data, and that's where automated tools and people power join forces. Machine learning helps sift candidates from false alarms, flagging interesting events much like a spam filter separates important mail from junk. Citizen science platforms let volunteers scan images for odd shapes or fleeting events, and between computers and curious humans, rare signals can be pulled out of noisy data. Coordination between different instruments is also key. A microlensing alert might trigger 10th ray, radio, and gravitational wave follow-ups, giving a fuller picture of a dark object's nature. Practical examples make the search feel down to earth. A wide-field survey equipped with fast cameras will notice a star's tiny brightening, prompting a narrower, high-resolution telescope to get a closer look. This is similar to a security camera spotting motion and a guard peeking through binoculars. Space missions devoted to mapping star positions can reveal invisible companions by tracking the slow dance of stars across the sky. And collaborations that stitch together radio dishes across continents behave like a single enormous telescope, achieving the sharpness needed to see the silhouette of a black hole's event horizon. It's astronomy's version of assembling a giant puzzle from many small pieces. Search strategies are constantly evolving as new instruments come online and data analysis improves. Surveys aim to be broad enough to catch unexpected phenomena, while missions with specific goals dig deep into promising regions. The overall approach is pragmatic: use multiple, complementary techniques because dark objects often announce themselves in different ways. Think of it as detective work: different clues, different tools, same stubborn mystery, but with fewer trench coats and more GPUs. Philosophical puzzles: darkness and the limits of knowledge. Some astronomical objects are so dark that we cannot see them directly, we detect them only through the way they tug on stars or bend light passing nearby. This is a core fact that turns ordinary wonder into a deep puzzle. When all we ever have are effects, how sure can we be about the cause? In everyday life this is familiar: a wet floor tells you someone trapped in rain, but it doesn't tell you whether it was the cat or a clumsy human. In space, the wet floor might be a streaking star or a warped beam of light, and the culprit may be something we cannot touch, see, or send a probe into. Philosophical puzzles arise from that gap between appearance and reality. We can map the pull of gravity and the bending of light, and from those data build models. But different models can sometimes fit the same observations. This is the problem of underdetermination: multiple explanations can match the evidence. A concrete example at home would be hearing footsteps in the attic. You might infer a raccoon, an old house settling, or a ghost. Each hypothesis fits the sound, but only more evidence will pick one. In the cosmic case, dark matter and modifications to gravity both try to explain certain motions of galaxies. Observations push us, but rarely force a single, final story. Another puzzle is about the limits of measurement tools. Telescopes and detectors only capture certain kinds of signals. They are like nets with a particular mesh size. You catch fish of certain sizes and miss the rest. Sometimes instruments record anomalies that later vanish under better scrutiny. For an everyday parallel, think of a smartphone battery that drains faster one day and seems normal the next. You can check apps and settings, but if the problem is a hidden software bug you cannot see directly, you are left making educated guesses. In astronomy we face the same detective work, but on a grander scale and with fewer clues. There is also a conceptual issue about what counts as knowing. If every direct route to information is blocked, do our indirect inferences constitute knowledge or just useful belief? Philosophers call this a debate between realism and instrumentalism. In practical terms, doctors routinely act on indirect evidence. A set of symptoms leads to a treatment that works even if the exact cause is uncertain. That pragmatic success can justify belief, but it leaves open the philosophical itch: does success equal truth? Sometimes yes, sometimes no. And that uncertainty humbles scientists and non-scientists alike. It also keeps science honest, because theories must remain open to revision when new kinds of observations arrive. Finally, the darkness of these objects forces creative thinking about limits and possibilities. We build better detectors, we search for indirect signatures like ripples in spacetime or tiny changes in the motion of nearby matter. We also accept that some regions may stay forever beyond our reach, much as a locked box hides its contents from us unless we find a key. Humor helps. It's a cosmic game of hide-and-seek where the universe is very stubborn and never checks under the couch. The philosophical lesson is practical: recognize where your evidence ends, be cautious in claiming certainty, and celebrate the clever ways humans find to learn from what the darkness lets them show. Future frontiers: what new telescopes might reveal. New instruments will be able to see fainter light and finer detail than before, opening a clearer window onto the darkest objects that hide in plain sight. Large mirrors collect more photons, which is like using a bigger net to catch more fireflies on a summer night. The more you catch, the more you can study patterns. Space telescopes that work in infrared light act like night vision goggles for the cosmos, showing heat and dusty regions that visible light cannot penetrate. Radio arrays spread over a continent behave like a giant ear that can pick up the whisper of slow, steady signals, while space-based detectors designed to feel ripples in space itself listen to the quiet thud of massive objects colliding. Sharper images will let astronomers watch how material behaves near black holes, the ultradense objects that pull in everything nearby. Gas and dust around a black hole form a spinning disk that glows and flickers. This disk can be likened to water swirling down a drain and splashing back sometimes. By watching those splashes with better cameras across different colors of light, 10th rays, infrared, radio, scientists can test how gravity and magnetism cooperate in extreme conditions. Coordinated observations are especially powerful. Combining light-based telescopes with detectors that sense gravitational waves gives a fuller picture, much like using both a camera and a microphone at a concert to know what instruments played and how loud they sounded. Mapping invisible stuff will also improve. When light from a distant galaxy bends as it passes a massive object, that bending acts like a magnifying glass, revealing the presence of mass that otherwise can't be seen. This effect, called gravitational lensing, can be used to trace where unseen matter sits in a galaxy or cluster. Upcoming wide surveys will collect millions of such lensing cases, letting researchers build detailed maps of invisible mass on many scales. Think of it as using many snapshots of a pond to understand where currents hide under the surface. The pattern of ripples tells you where something heavy just moved. Neutron stars and other compact objects will come into sharper focus, too, especially when different observatories watch the same event. Neutron stars are like city-sized spheres packed so tightly that a teaspoon of their matter would outweigh a mountain on Earth, and collisions between them send out both light and gravitational waves. Observing the glow, the radio afterglow, and the spacetime ripples at once reveals how matter behaves under pressures we cannot reproduce in a lab. That's similar to tapping a mysterious bell and listening to both the sound and the echo to figure out what it's made of. Unexpected discoveries are likely, and that is the most exciting part. New instruments often turn up objects or behaviors that theory didn't predict. A familiar analogy is how backyard stargazers sometimes find comets by accident when scanning the sky. Practical benefits may follow as well. Detector technology and data analysis methods developed for these telescopes frequently find uses in medical imaging and communications. Scientists and engineers will have fun arguing about what they see, and the universe will, as usual, keep its sense of humor by revealing things that force us to rethink once firm ideas. Cultural echoes, darkness in myths and science fiction. Many stories treat the absence of light as a character in its own right, a being that walks among people and changes their lives. In Greek myth, for example, night is personified by Nyx, a powerful figure who stands apart from more familiar daylight gods. In Norse tales the figure not rides across the sky in her own chariot, and in Japanese narrative the sun goddess Amaterasu once withdrew into a cave, plunging the world into total darkness until the other gods lured her out. These are not just spooky tales told to children. They are ways societies explained why the world suddenly goes silent and cold each evening, and they give a name and a face to something everyone experiences. The pattern repeats. When a culture wants to explain the unknown, it often frames darkness as a willful presence. Darkness also wears many masks at the human scale. It can be dread, like the shiver when a power cut leaves only the hum of the refrigerator, or comfort, like the deep hush that makes a conversation feel more intimate. A child's fear of a closet monster and an adult's fondness for midnight stargazing come from the same root, a brain that works harder when it has fewer sights to rely on, filling in blanks with stories. Rituals and objects then step in. Nightlights, lantern festivals, and bedtime rituals act like small treaties with the dark. People form practical rules, too. Never walk alone on an unlit street if you can help it, bring a flashlight camping, share a candle at a blackout, and those mundane choices are cultural echoes as much as the old myths are. Science fiction borrows this ancestral vocabulary and turns it toward the vast unknown. Black holes, for instance, are often used as modern stand-ins for the cave, the underworld, or the test you must pass. In plain language, a black hole is a place in space so dense that not even light can escape its pull, so storytellers use it as shorthand for an absolute limit or a doorway. Films and books use dark spaces to force isolation and introspection. Cramped, shadowy corridors in movies like Alien make fear physical. The deep, silent black of interstellar space in works such as 2001, A Space Odyssey turns emptiness into a philosophical mirror, and horror-tinged stories such as Event Horizon play on the idea that crossing a certain dark boundary brings something alien inside. When a spaceship drifts into a black void on screen, viewers feel the same old mythic suspense, only with more flashing console lights and oxygen worries. Writers and filmmakers often blend myth and science, reworking old symbols into future-facing meanings. The dark side, in Star Wars, is a direct reuse of the moral shadow concept from myth, dressed up with lightsabers and dramatic music. Ancient gods become aliens or advanced technologies in many tales. The cave becomes a wormhole, the night goddess becomes an inscrutable intelligence beyond human thought. Even product design follows the cue. Black packaging promises mystery, and film posters drenched in shadow signal seriousness or danger. This recycling isn't sloppy, it's functional. People already react to darkness in certain ways because of myths handed down through storytelling, and modern creators exploit those automatic reactions to make a scene land. The result is a cultural loop where old and new images of darkness reinforce each other. At the end of the day, darkness remains a versatile storytelling tool, useful for everything from simple scares to deep moral questions. It still tells us about fear, but also about privacy, comfort, and the unknown territories inside ourselves and outside our skies. And it's worth noting that while myths explain darkness by giving it names and faces, science fiction often gives it mechanics, how it works and what it does, while keeping the emotional meanings intact. So next time you switch off the lights to watch a space thriller or tell a ghost story by a campfire, you're participating in a long-running cultural conversation about what it means when the light stops. In short, we saw that the darkest objects in the universe come in a few flavors: black holes that trap light like a cosmic drain, neutron stars so packed a teaspoon would weigh like a mountain, invisible dark matter that acts like glue holding galaxies together, and dim objects like brown dwarfs and rogue planets that wander the dark like lost flashlights. Those are the main players, each strange, each different, and all a little spooky. If that surprised you, you're not alone. Space has a way of making our daily worries, like losing socks in the laundry, seem delightfully small. Thanks for sticking with me on this tour of the universe's moodiest residents. If you enjoyed the journey, please like the video, subscribe for more curiosity trips, and tell me in the comments which dark object you'd name if you discovered it. Next time we'll take a deeper dive, metaphorically, not literally, into what happens near a black hole and why time itself acts funny there. Hit subscribe so you don't miss it, and first we'll see you on the next adventure into the unknown.